Now we're going to look at the derivative by its definition, and I guess I want to talk just for a second about the derivative in general. Recall, the derivative in general is an equation to find the slope of a function. So here's some function, and I'd be interested in the slope, let's say between here and here. And I can approximate it by that, right? And we would do some delta y over delta x, and that would find us the slope between those points. And again, that's the kind of the average slope. Well, what does the derivative do? The derivative looks at shrinking those and getting super, super, super close. And really, again, this is the workable formula, but if you think about, all we're going to do is use a very sound algebra principle, which says that the slope m is rise over run. Delta y is the difference between two x values. So f of x plus h is the x value, is the y value here, minus f of x, and that's the y value here. Again, this coordinate point is some random x value, and it's on the curve, f of x. And this is some x value, x plus h. I just moved along the curve, h far, I added a certain amount to it, and then I got to a new y value, f of x plus h. And what I'm going to do, I'm going to subtract the two x values. And again, this is old school algebra 1, algebra 2. It says that the slope between 2 points is just y2 minus y1 over x2 minus x1. And so that's what I did here. This is the y value here. This is the y value there. X value, x value. And what we're going to do is, well, how do we make it calculus? Well, all we do is get these 2 points closer and closer and closer and closer to each other. And eventually, if we let h go to 0, instead of getting the average slope, right, the slope on an interval, we get the instantaneous slope, which is what the derivative is. And so the derivative by definition is going to be looking at how do we find these patterns? How do we develop, well, what is the derivative of a linear function or quadratic function? And if we do it, we can start to develop some intuition on what they should be. But I just want to remind you what a derivative was. All it is algebra 1. And again, this h, it just takes that x and they subtract them and cancel. And so the denominator looks like it's an h, but really it is just the difference between two x values. That difference is just h. Remember, you moved h over. So this h really is the run, where the difference here is the rise, and that's slope. So this is really just algebra 1, and we're just going to kind of go through with limits. So let's look at the first function, y equals 3x plus 4. Nothing too difficult, and I'll show you how we can figure out what the slope is. And again, I hope we know that the slope of a linear function is just 3, right? This is just y equals mx plus b. We know the slope is 3, so when we do the derivative by definition, well, of course, we better get 3, and I'll kind of show you how we can do that. So we want to look at the limit of f of x plus h. That's just taking x plus h and putting it in for x. So 3 times x plus h plus 4, that's f of x plus h, minus f of x, 3x plus 4, all over h. And we're going to look at the limit as h goes to 0. And if we multiply this out, this is 3x plus 3h plus 4 minus 3x minus 4. So you see how the 3x and the 3x cancel? And the 4 and the 4 cancel? And the only thing that's left over here, well, you know what? I'm going to write all that out. I won't skip any steps. We have that, and then minus 3x minus 4 all over h. We are still looking at the limit as h goes to 0. Now I'll go ahead and 3x and 3x, 4 and 4, and that's equal to 3h over h, but now h is cancelled, and I get 3, right? Which is the very predictable result. We knew that the derivative of 3x plus 4 is 3. The derivative is just the equation for the slope, and the equation for the rate of change, which we know for a line is just the number out in front of the x. Okay, let's do it for a little more complicated case. Let's do it for y equals x squared plus 1, right? This is a quadratic. A quadratic has a changing slope. So our slope, our derivative, better be some function of x, right? Here, this is just a line. It's just got a nice constant rate of change. So we get a constant. Here we better not get a constant. Okay, so let's look at the algebra. Let's look at the limit of f of x plus h. Again, that's taking x plus h and plugging it into the function. So that's x plus h squared plus 1. Okay, that's the first part. Minus f of x. That's just x squared plus 1 all over h. And we are looking at the limit as h goes to 0, right? H going to 0 mean our 2 points are just getting super close to each other. Okay, I'm going to multiply this out and I get x squared plus 2xh plus h squared plus 1. That's just me multiplying out x plus h, or foiling it if you like that word. And then I'm going to do minus x squared minus 1 all over h. And again, I am looking at the limit of this thing as h goes to 0. Don't forget you are applying the limit. Okay, x squared, 1, 1. And so we're looking at 2xh plus h squared over h. But now I can factor an h from the numerator and get h times 2x plus h over h. And I can cancel, and I'm left with 2x plus h. However, don't forget, you are applying the limit. We'll look at the limit of this as h goes to 0. 2x plus 0 leads us to a derivative of 2x. Okay, so I found the derivative using the definition of the derivative, not the power rule or any memorized pattern. I derived it from scratch, looking at this particular function and knowing that this is the equation for the slope given that. All right, I'm going to do one more. You know what? I'm going to do two more. I'll do a cubic function. So we did a linear function, a quadratic function. Now we'll do a cube. Let's look at y equals 4x cubed. And off to the side, I'm going to write the derivative of the definition again. It's the limit of x plus h minus f of x over h as h goes to 0. And again, this is just rise over run, and you're letting the 2 points get really, really close and looking for what the slope is. Okay, so this is 4 times x plus h cubed minus f of x, which is just 4x cubed, all over h. And of course, we are looking for the limit as h goes to 0. Okay, so we got to cube this thing. So off to the side here, you might want to do some work of what is x plus h cubed. You can do x plus h times x plus h times x plus h. You can FOIL that out. So you're going to get x squared plus 2xh plus h squared all times another x plus h, and FOIL all of that out. Or you can just know the binomial theorem, or you can look at Pascal's triangle. Your choice. You're going to get x cubed plus 3x squared h plus 3x h squared plus h cubed minus 4x cubed all over h. Again, the limit as h goes to 0. Okay, so I need to distribute that 4 into everything. So that's 4x cubed plus 12x squared h plus 12x h squared plus 4h cubed minus 4x cubed all over h. Okay, those are going to cancel. And all of these terms have an h. So I can factor an h and cancel. I won't skip any steps there. H comes out, leaving 12x squared plus 12xh plus 4h squared all over h. Those cancel. Remind yourself, you are always looking at the limit as h goes to 0, and now I can let h go to 0. When h goes to 0, that goes to 0, that goes to 0, and I'm left with 12x squared. So 12x squared is the derivative of 4x cubed. Again, I want you to start to think about a pattern. Again, if you took the derivative of a linear function, you got a constant. If you took the derivative of a quadratic, you got a line, right? It went down by 1 power, and look what happened when we took the derivative of a cubic function, we got a quadratic function. And you start to kind of build those ideas. I want to do one more example, and it's actually showing a trig function. So those were kind of polynomials, and those those kind of all follow the same format, but let's look at the derivative of a sine function, because I don't think all teachers probably even show this sometimes. Let's look at the derivative of sine. Okay, so we want to take the derivative of x plus h minus f of x all over, oops, as h goes to 0, over h. Okay, so what are we going to do here? Well, our function is just y equals sine x, and so we want to look at the limit of f of x plus h, so that's sine of x plus h minus sine x all over h, and we're looking at the limit as h goes to 0. And you don't really know what to do at this point. Well, it turns out that there is some angle sum identity. Angle sum identity that you have to use. And the angle sum identity, if you looked it up in a book, would probably be that sine of A plus B is equal to sine A cosine B plus cosine A sine B. Okay, and there's a proof of that. You can look that up as well. It's kind of a pretty cool triangle. I'm not going to go through that right now. Maybe I can make a video over that as well, but let's just trust that this identity is true, and I can make this substitution here. So I can rewrite this as sine x cosine h plus cosine x sine h minus sine x all over h. And again, we're looking at the limit as h goes to 0. Okay, so now I'm going to look at these two things, and I'm going to take a sine x from both of those things. So I'm going to take a sine x. From here, I'm going to leave cosine h minus 1. I'm going to look at that fraction, and then I'm going to look at this guy, and I'm going to take plus cosine x sine h over h, and I'm going to look at the limit of that as h goes to 0. And I think there had to be some time in your limit work that you decided that the limit of cosine h minus 1 over h as h goes to 0, that this is 0. And again, you're going to have to go through some, but that limit is equal to 0. This limit as h goes to 0 is equal to 1. Okay? And again, those two you hopefully looked at in a previous video or a previous section before you ended up looking at the derivatives. You looked at some limits, but those limits are 0 and 1, and so then sine x times 0 is just 0 plus cosine x times 1 is indeed just cosine x. And so what we just did there is we showed that the derivative of sine x is cosine x. Now, certainly, we can look at a graph and make the argument, there's my sine function, there's my cosine function, that the blue is the perfect descriptor for the slope of the red. And again, that's a pretty hefty discussion to have, but it does make sense that cosine is the rate of change of sine. Okay, so those are kind of your definitions. I did a line, a quadratic, a cubic, and then I even used the definition of the derivative to do a trig function.